Okay, so let's get going here. I'll be talking about what we're doing with Yarn at Microsoft. So to begin with, I spoke this morning briefly about some of this. We are really trying to deal with an environment where we are dealing with lots and lots of heterogeneous data and lots of heterogeneous applications running on top of this data, okay? Many with SLAs. So let's take an example. Here's a demo you can actually go see at the Microsoft booth that kind of brings all this together. So on the top, you see a ticker, right? That's actually processed, filtered data of a live feed coming from Yahoo. The filtering is done using Spark streaming. If you look at the left, you have a few more small news feeds. Several graphs in the middle. These are graphed based on the results of running NewSQL queries, which is like our version of high batch processing. And on the right, you see here a sidebar of things that you can click on that typically are the result of machine learning. In this example, we're using R on HT Insight. All the data, it's either streaming in live, that's the data behind this bar here, or there's 30 years worth of data sitting in Azure Data Lake backing all of this. All right. Now, you could go say, let me take a look at something that's happening here. And if you did, you'd be able to go play around with the results using Power BI. So all this is fully integrated with Power BI. And if you look in here, number of suspicious trades by location, by customer, so on and so forth, what you would expect. Or you could go take a developer perspective on this. I mentioned NewSQL. This is our query language. It also comes with its own IDE. This is an execution graph. It's actually live, so you can dynamically click into any one of those nodes, animate this to see the progression of your query, fun stuff. Or here, you can see the amount of data is at 30 years worth. It's about 8 terabytes, not a very large data set, but nonetheless, hopefully, you get a feel for the kind of environment we're talking about. Now, not only is this a rich environment with lots and lots of data, live and historical, there's a diversity of the types of compute and the modality, real-time versus batch. The scary thing, though, is the scale at which we do this day in and day out, right? If you take Microsoft, virtually the entire company runs on our big data stack. The amount of data, hundreds of thousands of daily jobs, thousands of internal developers, every day we have several hundred petabytes of I/O. The total amount of data managed in the multiple exabytes, right? The largest Yarn cluster that I'm aware of at Yahoo or Facebook is about 5,000 nodes. Our smallest cluster is an order of magnitude larger. We're talking 50,000 node clusters, right? Dealing with all this at scale is the challenge we set out to address. The underlying data is in our HDFS equivalent store. This is really what is evolving into HDFS Azure Data Lake. Okay? The thing I want you to keep in mind, in here, the data can reside in many tiers of memory in addition to the usual complexity you see in HDFS, where it resides across many thousands of machines. In our case, many hundreds of thousands of machines. Right? It could be in remote storage, it could be in main memory, it could be on SSD, it could be on local disk across hundreds of thousands of machines. And the exact metadata that says this file, this block is in this location, where location is much richer now, that's part of the name node equivalent. That's what we need to manage. With this, let's get to the main thing I want to talk about today. As we all know by now, it doesn't matter what job you're running in this environment. you will try hard to schedule your computation close to the data you're operating on. Moving the compute to the data works a lot better than schlepping the data someplace else, partly for compliance, partly because once you're dealing with petabytes of data, moving data around is expensive, right? We have individual jobs that run on 10,000 nodes and operate on individual tables on the order of petabytes, right? So, all right. The key here, if you want to deal with this level of heterogeneity on behalf of many, many users who want to share that data, you need to figure out how you can do resource management in this very heterogeneous, very multi-tenanted environment. For this, we have made a huge bet on YARN as the basis for our resource management. To be frank, YARN is not ready yet, right? We knew this, but we also felt this is a state-of-the-art where we want to contribute, work completely in open source, because it's a developer surface, and we wanted to be part of the community in here. And today's talk is all about what we are doing here. And everything I'm about to discuss, we are doing it completely as part of Apache projects in open source from the very get-go. Okay. Let's be very clear what we're talking about for those of you who may not be familiar with how this stuff works. I've taken two examples here, a relational query engine, a machine learning job. If you submit a relational query or a machine learning training job, what happens? Basically, on behalf of your job, there's an application master negotiating with YARN for resources of the kind it needs. The machine learning job may ask for GPU machines. The relational job may ask for data for containers that are co-located with where some of its tables are stored. All of this negotiation happens with the resource manager, in our case, YARN, the RM. And it's going to ultimately obtain resources somewhere in this tiered storage ecosystem where the jobs can run, okay? I mentioned uSQL. Well, uSQL is essentially the workhorse that our batch processing runs on at Microsoft. If you look at this, what we have done is to make sure that we align this with the way jobs run on Hadoop. This also, just like, say, Hive, right, goes through a resource manager, goes through YARN to obtain the resources it needs. There are a few other things, but this is the key point I want you to take away. It's no different from any of the other jobs in the Hadoop OSS ecosystem. So in the same way that you plug in Hive and Storm and let them run side by side, or Spark, you can plug in anything from Microsoft and it'll run side by side, multi-tenant. And this is the same story for our internal customers as well as our external customers. Okay, so what is resource management? Very briefly, it is the component that allocates containers to competing jobs of diverse kinds. From the standpoint of the resource manager, all the real estate for compute, by which I mean CPUs, memory of various kinds, right? On each machine, it's platted into containers. And these containers are all centrally managed. And when you have a job, the application manager for the job negotiates, gets the containers, off you go, you execute. Okay, and I'll say a little bit about where we are, where we perceive YARN at this point relative to some of the competition, but that's later in the talk. Some of the key gaps we saw when we started with YARN, there was no way to preempt, okay? If one big job is hogging up the resources, your choice either to kill it or wait. Neither of these is a good solution. So we did something called Amoeba to address this. There's now part of Apache 2.6, part of both the Hortonworks and Cloudera distributions. Another thing we are working on, scalability. Oops. If you look at YARN, as I said, maybe 5,000 nodes. We need to manage 50,000 node clusters. Clearly, there's an issue. We'll tell you what we're doing about this. Again, it's all Jira's, it's all an open source. You're more than welcome to jump in and contribute to these projects. or to consume these. Another issue, high allocation latencies. Yarn has this philosophy of centralized queue management, which is good because it gives you a global perspective on how your resources are being allocated to competing jobs. But then this also increases the cycle time for requesting and receiving a resource. In our own clusters, we had schemes where we were allocating locally at each machine, relatively independently, what was going on elsewhere in the cluster. Well, we're bringing these together, open sourcing the results as part of Yarn, right? Lastly, we are now working on a number of issues that come from wanting to have ultra-low latency interactive pools, right? Long-running topologies that run forever, essentially. And to do these, framework pooling, as it were, this is ongoing work. So everything from stuff that is in ideation to things that have already been pushed out to production through the various distributions, we are carrying out in the open source community in partnership with Hortonworks, Cloudera, many others in the community. Okay, here's the money slide. Here are all the different projects, all the different contributions. I'll give you pointers to lots of detail if you want to go follow up. Amoeba is the work on work-preserving preemption. Okay, I'll say more about this in a moment. Rayon is something we have done to allow for upfront capacity reservation. If you have a production job with an SLA and it's being run concurrently with best effort jobs, well, how do you make sure your production job finishes in a way that meets your SLA? Okay. Okay, Mercury and Yak. These are the things we are doing to improve allocation latencies. Federation, scaling up Yarn, framework pooling. This is the status of a spec. Federation, there's a prototype, there's a Jira. We're now pushing this out internally as well as into the wild. Mercury and Yak, similar. Prototypes, Jiras, papers. Amoeba and Rayon are both shipping. Okay, let's keep going. Amoeba. So, work-preserving preemption. What's the story? Let's look at this graph here, all right? If you look at the time on this axis and look at individual machines as rows, right? This shows the progress of a typical MapReduce job. Each row shows what's happening on some one machine. And what's happening here is life is proceeding peacefully until there's this straggler map job, okay? And what happens is, at some point, the reducers running on these machines get blocked, waiting for this straggler. That means all of this machine resource time is wasted, waiting for this straggler to finish, so that these are unblocked and they can proceed. Well, you can do better than that. If you were able to suspend that job without losing all the work, schedule other work on here, like so, right? And in fact, enable other map jobs to proceed in parallel until they get blocked, right? Then you can, in fact, save this. And if you do that, the gains are considerable, right? If you kill the job rather than suspend it because there's one straggler, that's wasted resources. The delta between this is about 30%, right? So this, we filed all the JIRAs. Ultimately, all this actually went out into Apache. In fact, this happened even prior or in the early days of my tenure at Microsoft. Prior to that, I was at Yahoo. Many of my guys, in fact, were part of the original list of authors of Yarn. Okay, so let's keep going here. All right, Rayon. This is work that really was done entirely at Microsoft after we moved there. And the goal is this. You have production jobs, and they typically are jobs that run for a long time, often batch jobs as part of production pipelines. They need to run regularly at a time that you know in advance, right? Every day at 3 p.m., let's say. Whereas the cluster is also heavily used by a number of other people continuously throughout the day. The utilization on our clusters is very high, okay? How do you make sure you maintain that high utilization while at the same time ensuring that jobs like this don't run into delays because the cluster happens to be busy? This is a core problem we addressed. And in a nutshell, there are two parts to the solution. We created a new resource description language which an application can use to describe what resources it needs when, right? It's your ask. Once your ask is accepted, and the system will do some level of admission control before accepting it, right? You're guaranteed that you will get the resource that you asked for. So I might go ahead, submit my job, or submit my request for capacity. Once it's act, I know that at the time stated, those resources will be waiting for me. Regular jobs, as well as SLA jobs, would go directly to the scheduler in the usual way that YARN works. Whereas with Rayon, best effort jobs still go directly to the scheduler. But these production jobs are going to go through a reservation phase where you're going to maintain plans of all the things you have pre-committed as well as what happens to be running at the moment. And given that global picture, you decide whether to admit a new request or not. Okay? And if you do this, I'm not going to go into this in detail, but this expression here, pictorially, this says, I need this amount of capacity for a certain window of time. Here, it's slightly richer. I need this amount of capacity for this window of time, this amount of capacity for this window of time, and both of these need to precede my request for this amount of capacity over this window of time. And as long as you preserve this partial order and give me these, I can proceed. So for example, if you're doing things like graph processing, which requires gang scheduling, these are the kinds of things that will help you. Okay, I'll skip the architectural details in the interest of time. Happy to talk to you later if you have interest. But let's get to the core results here. The bottom line, we were able to meet pretty much all the production job SLAs while considerably lowering the latency for best effort jobs, right? All while increasing cluster utilization and throughput. This work has been committed to the Hadoop trunk. It is, in fact, in the 2.6 release, part of both major releases. Okay. And if you look at this, here are the people who worked on it, lots and lots of JIRAs. I'm belaboring this point because oftentimes when I say we, Microsoft, are part of the OSS community, they say, really? Microsoft, open source? Guys, we are very much in this space. Okay, so if you look at SQL Server, for crying out loud, it now runs on Linux. On Azure, you can get HT Insight on Linux, right? Our goal here is to meet people where they want to be as opposed to dictating the platform they run on. And we're very serious about open source. In addition to Hadoop, we're also engaging deeply with R and with Jupyter, right? Jupyter notebooks. So let me keep going. And I can say all the things I want, but I think those JIRAs speak louder than words. YARN Federation. First off, as you all know, the scalability of YARN ultimately is limited by the centralized scheduling policy. And so the number of jobs, the number of nodes you have that you're scheduling for, the number of jobs, the number of containers for those jobs, the number of times you heartbeat, and if you don't heartbeat a lot, then latency increases, of course. All of this ends up limiting your scale, right? On the other hand, if you were able to scale with brute force, that's not a panacea. Like I said, we already operate very, very large clusters. And operations, maintenance, upgrades, man, this stuff takes forever. So a better architecture, in my opinion, is to have lots of smaller clusters, subclusters, that you stitch together to appear seamlessly as one gigantic logical cluster. From the standpoint of you writing a Yarn app master, the world is no different. Under the hood, it's dramatically different. So the benefits of this, by baking the smaller subclusters widely, you can reuse all of that and just add a layer for federating these clusters. That, among other things, opens the door to a lot of approaches to maintenance, where you can deal subcluster at a time, which is much more manageable. Lastly, there are opportunities to geo-distribute your computation. Who says all subclusters have to be in the same data center, right? So lots of exciting possibilities here. All right. So if you look at it, this is a high-level picture of what federation would look like. From the standpoint of your client, everything looks just like a standard Yarn cluster. By the way, oh good. Everything looks like a standard Yarn cluster. The policies governing how all this is managed can optionally look at your HDFS name node to figure out where the data is actually stored in this complex tiered storage world. You also maintain a state store that is the current best bird's eye view of what's executing across this whole data universe. You have these individual Yarn subclusters that are federated. Net of it, when you make a request as a client, as an app master, right, you don't realize that really the underlying cluster is a collection of subclusters. It all appears as one. Okay. Again, this work has not yet made its way all the way through the chute, but it's well underway and progressing nicely. Many JIRAs. There's also stuff that we have been rolling out. I think internally at Microsoft, we now run probably the world's largest Yarn clusters in the tens of thousands of nodes, and we are rolling it out to ever bigger clusters. Okay. Mercury and Yak. What are we doing here? Oops. So let's look at this little picture here. If you look at the duration of your average job, right, as job duration goes down, your average utilization also goes down. Why? The relative overhead of Yarn scheduling takes a bigger and bigger bite the smaller the job, and therefore the more jobs you're scheduling. All right? This tells you right away that allocation latency and overhead is considerable. There's a lot of room for improvement. Okay? So that's what these two pieces of work try and address. We began with Mercury, right? And this introduced distributed scheduling inspired by ideas from our own internal big data stack, which, as I said, we are in the process of now converging with the Hadoop Yarn ecosystem. The Yak work follows up on this, right, and does much more sophisticated queue management. So if you take Mercury, the key new idea is, in addition to the centralized queues for managing jobs, which Yarn has, at each node, the NM can maintain a local queue as well. And you have to blend these two intelligently. But if you're able to get into the local queue, in and out, bang, bang, you can really reduce the latency. But you have to make sure this doesn't interfere with overall utilization. And when you need to get resources on many machines, you do need to be able to do that as well. Okay? So the management of the queues across the main Yarn centralized queues and the distributed queues at each individual node, that's the focus of the Yak work. Taken together, what does all this give us? This is kind of how it looks. When you come in as a job and make a request, you would now be specific about your request. You'd say, this is a request that I want, either opportunistically or guaranteed, right? Guaranteed here means once I give it to you, I won't take it away. Opportunistic means I'll give it to you, but there is a possibility that my local decision, so I was able to give you a fast twitch response. Okay, here you go. But I haven't looked at the bigger perspective. And in doing so, the centralized scheduler may come back and override this local decision, right? So you declare what you really want, right? And if you're prepared to be preempted, then you say opportunistic, and typically the latency will be lower. But if you don't want to be preempted, you say guaranteed, and you'll go through the normal YARN process, okay? This is a nuance. It's not quite the same as upfront capacity reservation. Here, the job comes in and on the fly requests resources. And when the resources are returned, they are either guaranteed or opportunistic. In Rayon, you can say, I need these many resources carved out for me in advance of my job being submitted to you. Okay, so let's keep going. If you look at the results here, right, in a nutshell, if you look at stock YARN versus Mercury, these are the numbers for stock YARN. Here are the numbers for Mercury. Mercury is V1 of this work, right? Already you see some pretty significant improvements, right, in throughput. Now, once you introduce queue management, right, intelligent queue management, I'm not going to get into the details of the queue management here. There are papers I'll point you to if you're interested. The gains are even more significant. So these graphs are complicated, but I'll just give you the intuition. This is the duration of a job, the job completion time, right? And here you're plotting what happens, the cumulative distribution function of completed jobs. So as time goes on, with YARN, here's the number of jobs you were able to complete. With YAC, that gets lifted up, which is good. You're able to compute more for any given job duration you pick. The YAC curve is strictly better, all right? And more details here, YAC, Mercury, so on and so forth. All of these are available for you to go look at. Again, all this work was done completely in open source. Filed JIRAs, all this is going through various stages of the community voting process. Okay. So to summarize, let me recap all the different things I spoke about today. First off, starting with Amoeba, we have made it possible to take jobs and, if need be, suspend them and then later resume them in order to improve the overall scheduling in the cluster without losing the work already done when you suspend a job. Second, if you take Mercury and YAC, net-net, they improve task throughput and reduce latencies simply by being much more careful about queue management and introducing a new concept, local queues. Federation, we're just trying to go from clusters of 5,000 nodes to manage our fleet of hundreds of thousands of nodes. And some new work that I'm not going to really talk about for dealing with interactive workloads, for dealing with topologies for long-running storm-like topologies, essentially stream processing that never ends in principle. You need to think about things a little bit differently, right? And we are working on this. Again, we are working with many folks in the community, but this work is still at the status of specs. We are bouncing back and forth. We will very soon start filing JIRAs and contribute code. Okay, if you're interested in the technical details of what I have described, all of this is out there. a number of papers. I welcome you to go look at them. This particular paper is worth calling out. So this was done by many of us while we were still at Yahoo. This is the original YARN paper. Many of the other co-authors here are from Hortonworks, of course, and InMobi. Most of us were at Yahoo when this work was done. And many others that reflect the contributions I described that happened subsequently. Comparison. So if you take the state of the art here, right? Mesos is another open source resource manager that came out of Berkeley. These, Omega, Borg, these are the internal systems at Google. And Google, for a long, long time, has been doing resource management over very, very large clusters. All the cloud providers will need to scale, right? Sooner or later, this is a core challenge for us. At this point, I think it's fair to say that YARN is competitive with the very best out there, okay? Sometimes I use the phrase YARN++, just to say the version of YARN that we are running at Microsoft. Everything in YARN++ is open source. Our intent is, as soon as we bake things out, to push it out. So it's just a short step ahead of YARN, but converging. If you take reservations and planning, the Rayon work, YARN is the first scheduler to support these features. I believe the Mesos folks are already working on incorporating some of these results into Mesos. Queue management techniques, right? This is again new in YARN. Scalability, Borg is highly scalable. Mesos is, though it's a bit of an apple to orange comparison because they don't do scheduling at the level of individual jobs. They do it more at the level of frameworks. But nonetheless, I think we feel very comfortable that we can indeed scale. And some of the things like running across data centers, early days yet, very exciting. Now, remember the point I made about compliance boundaries. It's not just software. For many, many enterprises, us included, take Office 365 again, compliance boundaries mean that data created in one country cannot be moved outside of the boundaries of that country. But your analysis knows no boundaries. You may want to compare the profiles of folks in that country with your global population. How do you do things like this? There are no good solutions today. So these open up new worlds. One other project that I don't have time to talk about today. Reef is a layer that complements YARN. It essentially abstracts and supports control flow for YARN, right? And if you look at this, again, it's an open source project that Microsoft incubated. The project is there. The open source release happened in 2014. It's now fairly widely contributed to. We ourselves use it in a number of things if you're doing it at Microsoft. If you're interested, here are links. I hope you try it out, have a good experience, and hopefully start contributing to it. Let me pause here. I think we have about 5 minutes. I'd be happy to take questions if there are any. One here and then in the back, please.
In your slides to the federation, you had a small blue box saying HDFS placement hints. And did you do any work about, because if I would schedule a job to a global distributed cluster, it is very important to route the job to where the data is.
Absolutely.
So is there already work done, or is it something where you think about and doing papers and process?
Yeah, the answer is a bit of both. So if you take an individual job, absolutely you can and do get placement close to the data for that job, okay, right? But when doing the global planning, thinking about upcoming jobs as well as the instantaneous mix, now knowing about the resource profiles and making broader decisions, taking into account data placement. So you know that at 2 o'clock the workload shift is going to be with respect to some data sets. How does that impact your scheduling? This is still more at the futures stage, right? Yeah. In the back.
Sorry, this is more kind of a higher level, so more strategic. With you've got iOS, you've got SQL Server, the traditional Microsoft suite, you've got Apache.
Sorry, could you repeat? I didn't.
So you've end-to-end information services and SQL Server, the classic old Microsoft. You've got Apache, now you've got a SQL Server on Linux. I'm just trying to get a sense of where is this? Are they going to stay very separate? Or do you, what do you see in the future with how Yarn and SQL Server will work together, or the whole Microsoft stack and the open source stack?
Okay, so first off, simply the fact that SQL Server is now on Linux says volumes, right? But there's more. If you look at SQL Server 2016, R runs integrated into SQL Server. So in proc, as you're doing, as you're analyzing your data with SQL queries, you can also be doing R. If you take the polybase feature, it is integrated with HDFS, right? In terms of how SQL Server can utilize Yarn, yes, we are thinking about that as well, but there isn't anything concrete to share yet on that front. But what I will say is this. We have this bigger picture of where we see data and this space evolving. SQL Server has historically been extremely strong in transactional kinds of workloads, right? I think there's public information. It's a multi-billion-dollar annual revenue stream, right? It's by number of seats, the largest database by revenue, a close second, right? And if you look at the sheer footprint of SQL Server, clearly our strategy pivots around that. At the same time, we see the warehousing market set to take off because of all the things we have been hearing about all day, right? And we also see this as an opportunity to go into areas where the traditional database market has not been able to penetrate. Things like IoT, device storage. How do you capitalize on the strength we have in the traditional database segment, while at the same time also leveraging some of our assets like the big data stack internally, Hadoop, bringing them together? We're being very, very clear that we do want to bring these together. The exact details evolving as they go. In what you have already heard from me, I've kind of outlined how our internal big data stack is getting essentially aligned with the Hadoop stack. Our internal stack will look exactly like, it's an HDFS tiered store, built for the cloud from the ground up, but an HDFS store nonetheless. On top of this, all compute resources on those machines are managed using Yarn. On top of this, you can run the full complement of Hadoop tools, Hive and so on, as well as some of our proprietary tools, such as uSQL. And this last piece, your question translates into how do we see SQL Server playing into that, right? And I'll say nothing very specific to share yet, but stay tuned. Yeah. Other questions? Yes.
So you talked about having production jobs and sort of non-production best efforts.
Yes.
In the production job space, what do you have in terms of prioritizing them against each other? Because often you say, well, I want this to run at 3, and you can guarantee that, but in the real world,
It's a great question.
we need to run when this other stuff is finished. So you don't know exactly when.
Yeah, it's a great question. So again, the answer to this is it's very much work in progress. In one of my examples, I showed you a partial order. So I need this, and sometime later, I need this. Remember? You could use some mechanisms like that today. But that's not a knife that fits every job, every situation. right? And in general, having softer SLAs, expressing where you have a little more flex, and figuring out how to make this economically attractive to do, right? And if you think of spot pricing, that's an extreme. Give me the cheapest price you can, and if you need to kick me off, go for it. The other end of the extreme is, at this time, I need this, period. I need a guarantee, and I'm willing to pay for it. But what about that gray in the middle, right? We are very much working through this. This is where we hope, by making all this open, we don't have to do it all by ourselves. We can work together with the community to get the right ideas and the right contributions. Great question. Yeah?
You mentioned that this big data stack is part of your internal kind of ecosystem. Are any of these technologies used in Azure, like to manage the data by customers in Azure, or basically run ML Azure jobs or stuff like that?
Yes. So let me be very clear in case it wasn't. The store we are talking about is both our internal store and Azure Data Lake. It's available externally to customers as Azure Data Lake. The resource manager, YARN, is precisely what we use on top of both. So if you take a uSQL job, in fact, I had a slide where I showed what happened. That uSQL job is part of Azure Data Lake Analytics. When you submit that job, what happens is it goes through YARN on Azure to schedule your job on the right data lake machines close to your data. So yes, great. All right, thank you very much.